Although all Bronsted-Lowry acids contain protons, or H+, some acids readily or very easily donate those protons, while others do not. And some Bronsted-Lowry bases readily accept that proton, while others do not. How readily the proton transfer occurs determines the strength of an acid. Now, before we talk about acid-base strength, I want to distinguish that strength and concentration are not the same thing. So in a previous chapter, we talked about concentration, and concentration tells us how much solute we have in our solution. The strength of an acid tells us how readily it will donate or accept, if it's a base, the protons. So they're not the same thing. So let's try to get a better grip on what this strength is. So we have two big categories. The first category is the strong. So we have strong acids. So what strong means is it will readily or easily or eagerly donate, get rid of the H+. And when we're in water, it will 100% dissociate, and so all you have is ions. So strong acids, go for it. Now, strong acids is kind of a limited bunch, and the common strong acids are right here on this list. So we have HCl, HBr, HI, H2S, and HNO3. So these are called hydrochloric acid, hydrobromic acid, hydroiodic acid, sulfuric acid, and nitric acid. These are all strong acids, and they will readily donate their protons or 100% go to form ions when they're in water. If you're not on this strong acid list, then you are considered weak. If you have to study more chemistry, then it's good to memorize the common strong acids, and that way you'll be able to distinguish between a strong acid, because it's one you've memorized, or all the other acids, which would then be considered weak, and we'll talk about that in just a minute. Now you'll notice that the word strong base has a similar connotation, that word strong. So this bases accept protons, so a strong base readily accepts it, so it's going to take on the proton, and in water it will 100% dissociate into ions. So the word that they have in common here is strong, and strong means that it will readily do something, easily wants to do it, and or 100% dissociation. Now, just like strong acids, strong bases have a short list, and here's some of the common strong bases: sodium hydroxide, potassium hydroxide, lithium hydroxide, calcium hydroxide, or barium hydroxide. Now, if a base is not on that list, then it's not considered strong, and instead it's a weak base. So to reiterate, if you have to take more chemistry, then what's helpful is to memorize the strong acids and strong bases, since it's a limited list, and then you would know that if your acid or base that you're looking at is not on that list, then you have a weak acid or a weak base. So what does it mean to be a weak acid or a weak base? So it simply determines, or simply is determined by your ability, or the acid's desire, I guess, to think of it, to donate its proton. So weak acids less readily donate so they're not quite as willing to donate the H+. And when they dissociate, only a little bit of it forms ions. So quite a bit of it, when you're a weak acid, stays as the acid itself. And weak bases, notice the word weak, also are less readily going to do their accepting the hydrogens because they're bases. And again, in water, only a small fraction dissociate into ions. So the idea that distinguishes strong and weak: strong readily dissociate, readily donate or accept, and 100% dissociation. Weak are less likely to donate or accept, and only a small fraction dissociate to form ions. Now, one thing we can do with acid strength is predict the direction of an equilibrium. Remember, in an equilibrium, this is reactions that go back, they're reversible, they go back and forth. And at equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. We know in equilibriums that some equilibriums favor the reactants, some equilibriums favor the products, and there are those cases where you have a substantial amount of both reactants and products. Well, the strength of the acid helps us to determine if an acid-base reaction will favor the reactants or the products. Here's the overarching idea. The stronger acid reacts with the stronger base to form the weaker acid and the weaker base. So, to break that down even further, where will the equilibrium be? The equilibrium will favor or lie on the weaker side. So in order to predict the direction of the equilibrium, we have to decide which side of our reaction is the weaker side. To answer these types of problems, we use a chart that's similar to the one here. And this is found in your textbook, and we don't need to memorize this. Let's look at the chart first, and this is not an extensive chart, it's only selected acids and bases. So looking at the chart, what you'll notice is that on the left side here are the acids. And if you follow the arrows, it goes up. And in this case, the strongest of the acids are on the top, and the weakest of the acids are on the bottom. And what you would notice about their conjugate bases, or their partners, so here's the conjugate bases, is it has an inverse, has an inverse effect on the strength. So at the top, sorry, I'm hitting the button that changes the page. Oh my goodness, sorry. I'm not going to write weaker up there. And these are stronger down here. So it's the opposite. Let me erase this weaker and see if I can't write it further over. Okay. So you see the relationship. The stronger the acid, the weaker its conjugate base. And the weaker the acid, the stronger its conjugate base. So let's see how we can use the strength of the acids to figure out if a reaction favors the product side or the reactant side. So let's follow, and we're going to use this table. So step 1, label the acid on the reactant side and the conjugate acid. So notice that I'm finding out the acid and the conjugate acid. So in my first problem, looking here, HF is the acid, and then so that means this would be the conjugate base, this would be the base, so then the water is the conjugate acid. So we see I labeled those two. Then we go on to the table and find those acids. Now, we're looking on this side of the chart because we're looking at acids. So in this example, we're not going to be evaluating based on the conjugate base side. So I find HF, and I'm looking right here. And I find water, which is down here. And so since it's stronger at the top, I know HF is stronger, so I wrote stronger. And water's way down here, it's weaker. So if you recall, the equilibrium favors the weaker side. So this is the weaker side, which is the products. So this reaction favors the products. So let's try the next one. I'm going to get a different color so we can distinguish. Okay, so looking at this second problem here, I don't like that color, it's too dark. So I'm looking and I see that the H3O plus goes to H2O, so this is the acid. And that would make this the base. This is the conjugate base, the acid. And so if this is the base, when it accepts an H plus, this is the conjugate acid. The conjugates are always on the product side. So now I find it, and you can go back and practice. We discussed acids and conjugate bases, pairs in a previous video. So let's see, I'm going to look for this acid, H3O plus, which is right here. And for the conjugate acid, which is H2CO3, which is right here. So this one is stronger, the H3O plus. So that guy is stronger. And this one is weaker. So the weaker one is the conjugate acid. So it favors the side that's weaker. So this would favor the products. So let's try one more. And then you can try it and let me know if you have trouble. So labeling, we want to label the acids, and we get that NH4 plus is the acid. And so that means this is the acid, this would be the base. So then this is the conjugate base because it's the partner with the NH4, and this is the conjugate acid because it's with the chloride ion. So now these are my two. So I find NH4 plus on my chart, and it's hard to see because I wrote there. It is right here. And then I find HCl, which is a strong acid. It's way up here. So this is the stronger acid, and this is the weaker acid. So the weaker acid is on this side. So it favors the side of the weaker acid, and so this favors the reactants. So in order to determine the equilibrium in an acid-base reaction, or which side is favored, first you label the acids and the conjugate acids on the reactant and product side. If you have to label the base and the conjugate bases, that's fine, but we're going to evaluate the acids. The second thing you do is compare the acid strengths using a chart such as the one on the right. And then what you have to remember is that the equilibrium will always favor the side that contains the weaker acid. You could also evaluate the bases and the conjugate bases, but you would have to use this side of the chart. And there again, the side that would be favored would be the weaker side. And in both cases, the weaker side would be the same side, so you wouldn't make a mistake that way.